Good afternoon, ladies and gentlemen. Thank you for joining us today for the webinar titled Cerro Verde Mine Tailings Storage Facility, presented by Jim Obermeyer and sponsored by Stantec. SME appreciates the outstanding contribution of Stantec as a sponsor, which allows us to offer this webinar complimentary to our attendees. My name is Jackie, and I will be serving as your host for today's session. Attendees may submit questions at any time during the presentation by using the chat panel. I will read the questions aloud to our speaker during the question and answer period following his presentation. This webinar summarizes the collaborative design and construction process of a new tailings storage facility at the Cerro Verde mine that took place from 2008 to 2015. Jim Obermeyer is Senior Vice President at Stantec and has managed numerous tailings storage facility projects involving the full life cycle of the mine. I'm now pleased to turn our session over to our presenter. Jim, would you share your screen with us?
Okay, I thought that I was sharing. Okay, gotcha.
Perfect. Please proceed. Yes, sir. Please proceed.
Okay. Thank you, Jackie, for that introduction. I'm going to be speaking today, as Jackie mentioned, about a collaborative design and construction process of a new tailings storage facility at the Cerro Verde mine. The work took place from 2008 to 2015, and the Cerro Verde mine is located in the southern part of Peru, and it's about 30 kilometers south of the city of Arequipa. I'd like to acknowledge the co-authors of the paper that was presented at SME in February. Amanda Adams, who is a colleague of mine at Stantec, and three individuals from Freeport-McMoRan, Teresa Spiegel, Tamara Jandro, and Shane Wiegand. So thank you for your contributions. I'm going to emphasize today how a close partnership between Stantec as the designer and engineer of record, the mine owner and operator, Sociedad Minera Cerro Verde, and its majority shareholder, Freeport-McMoRan, facilitated a robust design and an efficient project execution. This photograph shows the starter dam in its final stages of construction. It's viewed from the left abutment looking toward the right. You can see here the startup water pond on the upstream side of the dam. You can also see that the jacking header system to support the tailing delivery system is in process of being installed. And so this was representative of what was happening in September of 2015. This slide speaks to some of the project challenges and solutions that we had on the project. The design production rate was very high at 240,000 tons a day, and that challenge was addressed primarily by identifying a very large and efficient site. Second, the Cerro Verde mine is located in an arid desert environment with scarcity of water, and this required a water efficient design and a detailed water balance model that was used to define the makeup water requirements over the project life. Next, the mine resources required an exceptionally tall dam to store about 2 billion tons of tailing materials. The ultimate embankment height is going to be 305 meters at the center line and 435 meters above the downstream toe when it's completed. The starter dam itself was 165 meters tall at the center line and about 200 meters above the downstream toe. And this dam height challenge required specialized modeling and material testing and extensive foundation characterization. Fourth, the site's located in one of the highest seismicity regions of the world, and this was addressed by an experienced design team with the use of sophisticated design tools and with sound advice from an exceptional review board that consisted of Dr. Andy Robertson, Dr. I.M. Idris, Dr. Gabe Fernandez, and Dr. Leslie Smith. Fifth, there was no ready source of low permeability material for core construction. That's a considerable problem when you're building a dam that's designed to store fluids. And finally, the permitting and construction schedules were very tight, and the solution to this challenge was extensive planning by a seasoned project team that was led by Freeport-McMoran's projects group with collaboration from Stantec and the Cerro Verde operations team. I want to point out the existing facilities and the proposed facilities at the Cerro Verde mine. This is the C1 concentrator. This is the Quebrada Anlazada tailing storage facility. Both of these facilities, the C1 concentrator and Anlazada, were commissioned in November of 2006, and the C1 concentrator has a throughput capacity of 120,000 tons a day. This is the Cerro Verde pit. This is the Santa Rosa pit. This is the C2 concentrator location and the Quebrada Linga tailing storage facility. It's these two facilities that were that were included in the Cerro Verde production unit expansion project, which included a 240,000 ton per day concentrator and the Linga facilities. One other part of the project that I'm not really going to be talking today about was a wastewater treatment plant that was designed and constructed as part of this project. It treats the municipal waste from the city of Arequipa with a population of about 1 million people, and part of the effluent from that wastewater treatment plant was used for to provide makeup water to the C2 concentrator. A bit of a project overview and a look at the design criteria. The ore type is porphyry copper. The reserve at the Cerro Verde mine at the time of this project was 3.4 billion tons. Production, as I mentioned, 240,000 tons a day. The total life of this facility is 24 years, and the startup water requirement was 2 million cubic meters. The tailing embankment is designed to handle the probable maximum flood. The probable maximum precipitation depth is 464 millimeters, and the runoff from that storm produces a volume of 19.9 million cubic meters. The facility is also designed for the maximum credible earthquake. We considered 2 earthquakes, both large. One, the interface or subduction zone earthquake with a magnitude 9.0 and a PGA of 0.32 G. And the second, an intraslab magnitude 8 earthquake with a PGA of 0.67 G. We adopted a minimum static factor of safety of 1.5 as the criteria, post-earthquake factor of safety of 1.2, and we had a design freeboard of 5 meters. Also, the zero discharge concept was adopted for the tailing storage facility. There's a seepage collection system that's shown in this photograph, the lower right, and it's designed for an assumed power outage of 12 hours because the water here is evacuated with a pumping system. and it's designed to store the runoff from the 200-year 24-hour storm. And there's a spillway here on the left abutment that's sized for the 500-year 24-hour storm. The project engineering and design phases of the project spanned a 5-year period from 2008 to 2012. And it began with a scoping study, site selection study that considered 12 potential tailing dam sites that were within reasonable proximity to the Cerro Verde mine. Those sites were then reduced to and prioritized so that we evaluated 3 sites during the feasibility study in 2010. And that led to selection of the Quebrada site that we're going to be talking about today, with basic engineering done in 2011 and final design in 2012. Embankment types that were evaluated during the feasibility study were, we kind of shortlisted those to 2, and one is the downstream method rock fill, and the second is a centerline sand embankment. It led to, and really those 2 were ranked almost equally. And so how do we make the decision? The tiebreaker really involved 3 factors. One was the excellent performance of the Quebrada and Lozada TSF, and that TSF is shown on the photograph here on the right. It had been in service since 2006, so there was comfort that things were working well and the dam was performing well. Second, water efficiency. We were experiencing water use, makeup water of 0.38 tons of water per ton of ore, which is exceptional. And the predictions that we had for water requirements comparing the downstream method, rockfill dam with centerline, sand dam embankment, indicated considerably better performance from a water efficiency standpoint for the centerline sand embankment. And then finally, experience of the mine operators with the construction method. They had been operating now the Quebrada and Lozada tailing storage facility for several years and were comfortable with that construction method. So that's the one that got carried forward. The next several slides are going to summarize the investigations performed and provide an overview of some of the aspects of the engineering and design of the Quebrada tailing storage facility. Just to put things into perspective from the size standpoint, this is a graphic illustration in comparison of the ultimate height of the Quebrada tailing storage facility at the center line, 305 meters, compared to some well-known structures, the Washington Monument, the Eiffel Tower, and the Empire State Building. So this is truly a huge earth embankment. If it were to be completed today, it would be the largest earth embankment in the world. I want to speak to the material and water balance. They were fundamental to the success of the project, and we began with a material balance model that had 1-month time steps over the entire 24-year design life and was used to select the starter dam size and the cyclone station capacity. And it was that that part of the study that determined that the starter dam needed to be 165 meters tall at the center line. And it determined also that the cyclone station needed to be able to handle half of the feed from the concentrator in order to be able to produce enough sand to maintain the embankment crest elevation with sufficient freeboard above the impoundment. And so what we found was that we needed to cyclone 50% of the 40,000 tons per day or 120,000 tons per day that needed to go through the cyclone station. Here you can see a figure that was a direct result of the material balance, elevation versus time for the embankment, and then a plotting of the impoundment elevation. So once we finished the material balance, the water balance modeling was done. It was also done in 1 month time steps and was actually directly linked to the material balance in order to estimate the makeup water requirements over the entire 20-year project life. In this photograph, you can see the reclaimed barge system. There are 2 floating barges in the reclaim pond. Each of those barges is equipped with 4 vertical turbine pumps. The water is pumped, part of it is pumped back to the process plant for reuse, and the other part is delivered to the cyclone stations for use as dilution water. We have 2-stage cycloning to central cyclone station. Here you see that there are 2 banks or clusters of primary cyclones, and these clusters include a total of 60 15-inch cyclones, and they're also equipped with a cyclo-wash system. The secondary cyclone station is shown in this photograph, and it consists of 13 26-inch cyclones. This slide shows the geologic interpretation of the site. I guess I just want to stress what I believe is such a fundamental and an important part of the design of a tailing storage facility, particularly design of a safe tailing storage facility, involves the need to understand the geomorphology of the site and the geology of the site and the geotechnical characteristics of the materials. On this photograph, you can see here an outline of the starter dam footprint, and here in this larger footprint is an outline of the ultimate height embankment. The main rock types in the embankment foundation are intrusive igneous rocks. You can see that there are diorites, there are monzonites, monzodiorites. There are also a number of tuff deposits that we referred to on the project as tuff pods. Inconveniently, one of those tuff pods is located on the axis of the starter dam, so we had to deal with that. I'll be showing you a little bit about that during this presentation. But you can see these other pink deposits. This one was also within the footprint of the starter dam, and then we have tuff pods downstream that are within the footprint of the sand embankment. We have granites upstream, and we established a rock quarry in this location to quarry rock for use in constructing the upstream shell of the starter dam. And we had a second rock quarry in the intrusive igneous rocks downstream of the dam in this location. And I'm going to talk about how important it was to have 2 quarries for this project. In this photograph is a view looking upstream from the downstream quarry. The starter dam crest is superimposed on this photograph. This is the left abutment, the right abutment, and you can see this tuff pod that I was describing on beneath the axis of the dam. Here's a view turning now 180 degrees and looking downstream from the upstream quarry. Again, the starter dam crest is superimposed. This is the right abutment, left abutment. We did detailed geologic mapping to understand and define the characteristics of the geology at the site. And then we implemented a subsurface investigation program between the years 2008 and 2011. We started out in 2008 to 2010 with 39 drill holes. in the area of the Linga TSF site during the feasibility study program. We added 53 additional drill holes at the project site during basic engineering and final design in 2011. We had a total of 17,163 meters of seismic refraction surveys, and we made 28 MASW measurements. Those were along the dam center line, at the seepage collection sump, and at ridge lines and unique geologic features like the tuff pods. And we also used those seismic refraction surveys to help us identify optimal locations for the drill holes. In addition, we had 93 test pits, road cuts, and stream channel cuts that were all logged and sampled between the feasibility study and detailed engineering. And most of those test pits were used for borrow investigations. I mentioned that clay borrow sourcing was one of the considerable challenges for the project. There were no significant sources of clay present in the overburdened soils at the site where we normally like to get our clay core materials, and we needed an estimated 1.6 million cubic meters of low permeability in the central core of the starter dam to meet the design objectives. So from where would we find this material? And we met with Cerro Verde geologists, and their geology team noted that there were hydrothermal argillitic alteration zones of granodiorite porphyry within the leach cap rock, which was positioned above the economic ore deposit on the west side of the Santa Rosa pit. So the geologists believed that those zones of leach cap rock might be a source of the clay material that we needed for the project. But how are we going to prove that? We coordinated closely with the geology department. We examined thousands of meters of core. We characterized the total clays. We characterized the swelling clays, and we characterized the quartz and the unconfined compressive strength. And all of those were factors that contributed to the suitability of the material for use as a low permeability core product. And so once we found the material that we thought would work, what we did is we implemented a test fill during the design phase to prove whether the material was, first of all, could be excavated and reduced to the sizes that it needed to be. Essentially, we were converting rock into soil material that was going to be used in the critical component of the dam. And the test fill indicated that we indeed could produce the material we needed. And then we defined what would be the processing requirements and how were we going to identify the material at high rates of production in order to efficiently provide it during construction. And what we did was we logged the drill cuttings, and the main parameter that we were looking for in the drill or blast hole cuttings was the Atterberg limits. That was the most critical parameter and the easiest to identify as being suitable or unsuitable. Then we determined that we wanted to have a maximum size for the clay materials or the clay core of 15 centimeters. That led to a need for processing, and you can see this processing operation in this lower left photograph. So once the material was indicated by the Atterberg limits to be the right material for a core, the Cerro Verde mine increased the powder factor and the fragmentation of the material that was produced. Then the haul trucks hauled the material to a stockpile, and we used power screens primarily, but some grizzlies to screen off the plus 15-inch particles. So the next issue that we needed to address was, since the material was so dry after the screening process, we had to devise a method to add moisture to the material. And we'll credit the Cerro Verde leach pad operators with the system that they came up with. This is shown here. This is in a small stockpile located near the starter dam site, and it's a system that was adapted from Cerro Verde's leaching operations. And what we did was applied water to the surface for a minimum period of a month, and we found that that time was necessary for a couple of reasons. First, to uniformly add moisture to the stockpiles, and secondly, another important benefit was that by hydration, we were able to increase the percentage of fines in the material. So that 1 month period of adding moisture was found to be very important. And interestingly, the retained moisture content in this material was very, very close to optimum moisture content. And what we found was that once we excavated and hauled this material to the fill surface on the dam, we only had to make very minor moisture adjustments in order to achieve the specified moisture for placement and compaction, which was between optimum and 2% above optimum. Here you can see a photograph of a Caterpillar Model 825 compactor. That's what we used in the production phase of the project. We actually had 2 of those 825s on the fill surface in order to be able to maintain the required production rates. In the way of an overview of the specifications for the core, the liquid limit minimum was 20. We had a minimum plasticity index requirement of 10, a maximum size of 15 centimeters, and a minimum fines content of 15%. And that was for the bulk of the material. But we also had what we call the select core material that was specified for the abutment contacts and to backfill the cutoff trench, where the maximum size was limited to 1.5 inches and the minimum fines content was specified to be 20%. And our objective here was to develop a finer material with a higher fines content that would develop a good bond with the bedrock at the abutment contacts. Now I just want to do a quick summary of some of the material testing and deformation modeling. For the testing, I'm going to concentrate on the underflow. That was the primary material that we characterized, although every zone was characterized as well. I just don't have time to cover all of that in this presentation. We used remolded samples of underflow from Quebrada on Lazada for this laboratory testing, and the underflow was tested using both static and cyclic triaxial testing at low to high confining pressures. And we were looking to evaluate the shear strength and the potential for particle breakage with these tests. We used cyclic DSS testing at low to high confining pressures to measure shear strength and to evaluate liquefaction potential. We used combined resonant column cyclic torsional testing to develop modulus reduction and damping curves for the underflow. And we did shear wave velocity testing at varying confining pressures. Now, once the laboratory testing program for the underflow as well as the other zones of the dam was completed, we did static deformation modeling using FLAC 3D, and we did seismic deformation modeling using FLAC 2D. The static deformation modeling was done mainly to evaluate the potential for low confining stress zones at the abutment contacts and to assess the possibility for hydraulic fracturing of the core at the abutment contacts. And of course, we also looked at other issues that could develop in other parts of the core. But we were primarily interested in deformations of the core in this static modeling. And we modeled 3 stages of the TSF. We modeled first the starter dam alone, and then we modeled the embankment after 2 years of operation with some additional, with some underflow added to the downstream shell. And then third and finally, we modeled the starter dam and the ultimate height embankment. And what we found was that we had predicted deformations that were within tolerable limits. We found that we didn't have these concerning reductions in confining pressures at the abutments, but we did design a system including 4 shape acceleration arrays to measure the deformations in the field, and those actual measurements have compared very favorably with the results from the static deformation modeling. The seismic deformation analysis was done with the objective of estimating deformations that would occur under MCE loading and to evaluate if internal features like the filters and the drains, for example, would be compromised, and to assess the freeboard requirements. The results of the seismic deformation analysis indicated that expected deformations were well within tolerable limits, and that the design freeboard of 5 meters would be adequate. Now I want to talk a little bit about the starter dam construction. Here's a cross section of the starter dam. The upstream slope is 1.5 to 1. Downstream slope 2 to 1 in the upper portion and 3.5 to 1 in the lower portion. And of course, these flatter slopes are not determined based on stability analyses. They had to do with operational considerations, and in particular, the 3.5 to 1 slope is a starter slope for placement of the underflow, and it corresponds with the angle of repose for hydraulically deposited underflow material. And if this slope was steeper than that, it would tend to just flow down to the toe, and it would be unmanageable in terms of spreading and compaction. So that's its purpose, and part of the purpose here is to reduce the amount of underflow that we needed to produce to get up to the starter dam crest. But also we need to be working on some of these slopes, and a slope of say 1.5 to 1 would have made that much more difficult. Talking a little bit about the zones, we have rockfill zone 1 in the upstream and downstream zones. On the upstream side of the core, we have an upstream transition zone that's 8 meters wide. Zone 3 is the bulk of the core. This is the material with a 15 centimeter maximum size. Zone 4 is the downstream face veneer that separates the underflow that is deposited, and it prevents migration of the underflow into the rockfill. On the downstream side of the core is the downstream transition filter, and then downstream of that is zone 6, the downstream transition drain material. Here you can see zone 7, that's the select core that's used to backfill the cutoff trench, and also it's placed against the rock abutments all the way up to the top of the core. The cutoff trench had a bottom width of 10 meters, 1.5 to 1 side slopes, and it penetrated 5 to 7 meters into the competent rock, or fairly competent rock. You can see here that zone 5 filter and zone 6 drain extends downstream, and this distance is 80 meters. And that distance was defined by seepage modeling, where we had gradients that indicated that we had a need for filter and drain materials. And in addition, you can see these 2 lines represent a cutoff trench, or a grout curtain beneath the cutoff trench. These photos show the abutment preparation in the right abutment and the left abutment. And I wanted to talk about that because of the importance of getting this right in the construction schedule. All of this foundation treatment for excavating the cutoff trench and foundation preparation beneath the core needed to start at the top of the abutments and then proceed down to the bottom for safety reasons. So that was the case in both of these abutments. So that work was on the critical path. We were able to do foundation preparation in the downstream rock fill zone, place the drain there, and place some rock fill to kind of get a head start on this rock fill placement downstream in parts of the valley that were very tight. But the rest of the earthwork had to wait basically until we got this excavation complete and until we could get backfill started. Here you can see this is the initial core placement in the cutoff trench. We're looking here toward the left abutment, and you can see forms in place for a grout cap prior to grouting in this location. That grout cap actually went up the abutment further. But all of this was on the critical path and needed to be figured into the scheduling. Not to mention the fact that we had this large tough pod located on the left abutment, and that tough pod had a thickness of 20 meters. We had to excavate through it into the underlying intrusive igneous rocks to get a cutoff into the more competent rock. There were joints and seepage concerns in the tuff. So a little bit more about foundation preparation and grouting. The characterization of the foundation indicated that we had a need for 3 types of foundation treatment: type A, type B, and type C. Type A was in competent to moderately fractured rock. Type B was in moderately to highly fractured rock. And this material in type C foundation consisted of hydrothermally altered rock, faulted rock, and highly fractured rock. Foundation type A was designed to have 2 rows of grout holes, 10 meters deep. The central row, type B has 3 rows. The upstream and downstream lines of holes are 10 meters deep, and the central row is 5 to 10 meters deep, depending on grout takes in the upstream and downstream rows. And type C, this is our poorest rock, required a reinforced grout cap and 3 rows of grout holes. The upstream and downstream lines of holes are 5 meters deep, and the central row was 10 to 15 meters deep, depending on the grout takes in the upstream and downstream rows. The spacing for the primary holes in all 3 types of foundation was 5 meters on center for primary holes, and then we had secondary provisions for secondary, tertiary, and higher order grouting where needed. The foundation preparation also included dental concrete. You can see dental concrete placed here to smooth the surfaces so that we could get good contacts with the clay core material. And we had slush grouting to treat these joints that you can see in the photographs here, joints and fractures and openings. They were all treated by slush grouting, and we had particular specifications for different configurations and sizes of openings. This table shows the starter dam construction quantities. As you can see, the total fill volume was a little over 13.7 million cubic meters. I talked before about 1.6 million cubic meters for the core. This was the bulk of the core, about 1.5 million cubic meters, with the 15 centimeter maximum size, and the select core was about nearly 85,000 cubic meters. This is with the 1.5 inch maximum size material. And as you can see, the total rock fill volume is about 1.7 million cubic meters. And the rock fill placement rate generally controlled the construction schedule, although production of filter and drain materials also became critical at times. And of course, the foundation grouting had to be managed to keep it off the critical path. The duration of the construction schedule was really defined by the time that the date on which we were permitted to start construction, which was May of 2013, and the date when the new concentrator was scheduled for commissioning, which was September of 2015. However, the starter dam had to be completed 1 month earlier than that in August of 2015 to allow a month for jacking header and pipe installation on the starter dam crest. So what we ended up with was a total of 27 months of construction to complete all activities for the starter dam, including the foundation excavation, grouting, the material processing and production, and the dam embankment fill placement. So I thought it'd be interesting to show the rock fill placement rates that were actually experienced on the project. And as is the case with most construction projects, the placement rates are slower at the beginning and they're slower at the end when the available surface area for placement of the material is limited. And then we peak in these production rates somewhere in the middle. That was the case here, and we peaked at a monthly production rate of 1,070,000 cubic meters in the month of December of 2014, and that corresponds to a daily production rate of 34,500 cubic meters. That's a lot of material to be handling, and it took 24/7 for the entire construction duration to be able to do that. I want to speak a little bit to the photos in this photograph. Heavy mine trucks were used to haul the materials from the upstream and downstream quarry to the rock fill. At the peak, we had 14 haul trucks, and they were a mix of Caterpillar model 793 and 789 haul trucks. The 793s have a capacity of 240,000 tons, or 240 or 250 tons, and the 789s 189 tons. After getting the material to the fill, we added 8% by volume before compaction of the rock fill. Here you can see a photograph of an excavation for a water replacement density test. We used the same pits also for field permeability tests of the rock fill. And in this photograph, you can see the fill surface with the core here, the downstream filter and drain zones, the rock fill, upstream transition, and the rock fill. I do want to talk a little bit about some of the success factors for completing the project on schedule. It doesn't happen by accident, and I'm going to talk about 8 factors or so. One of those was that there was a very strong construction management team for monitoring, working with contractors, coordinating contractors with the Cerro Verde's heavy earthwork construction fleet. There was detailed planning and sequencing of all of the activities. For the embankment itself, we split the embankment every 10 meters in elevation difference and estimated the quantities for every 10-meter slice that had to be constructed. And that defined what the production rates for every one of the zones needed to be to complete construction for every 10 meters of the embankment. And it was also used to establish then what KPIs were, what the sizes of the fleets needed to be, what the production rates needed to be for filter and drain materials and so forth. So that was a key element of the planning. There was collaboration and cooperation between Cerro Verde for self-performed construction with the large mine equipment, with Freeport Corporation for project support, and with the design team for technical support. Use of the large mining equipment was absolutely essential for meeting the required production rates. Having the upstream and downstream quarries was critical. We needed a quarry to provide the rock fill to the upstream zone that was taking independent haul routes to the upstream face, and we didn't need to be crossing the core with heavy haul trucks. And then to have the downstream quarry for providing rock fill for the downstream rock fill zone. We needed to be responsive to contractor requests for technical information and responsive to the changes in site conditions that often occur with dam construction and require attention immediately in order to avoid delays, and we needed to have QA/QC testing that was rapidly done to avoid delays. We identified that specialty contractors were needed for parts of the work, and in particular for the foundation preparation, for the grouting operations, and for the aggregate material processing. And finally, it was critical that we had Cerro Verde's ability to source additional equipment to maintain or recover schedule in cases where that was required. Now what I'm going to do is show 27 months of construction in 46 seconds. What I have here is a time-lapse video, and first I'd like to orient you as to the site. The center line of the starter dam crosses the valley about in this location. Up here we have the downstream quarry, so we're looking downstream. And I would like to just point out a couple things to watch for in the video. Watch the changes in the haul road locations. You can see this particularly well in the foreground of the photo. Many of the haul roads to the downstream zone are behind this ridge, so you can't see those quite as clearly coming up. So you can see that, and I'll try to call a few other things out. You'll notice that the downstream rockfill zone was placed before we got started with backfilling the cutoff trench. So you'll see that in this area. It happens kind of fast, so I thought I'd try to get you oriented to the site in advance. So here we go. You can see that rockfill being placed down here. You're going to soon see some. Now you see some reddish brown material. That's the core construction. It's coming up. Now we're approaching a level surface with almost the entire dam embankment. Here you can see those haul roads I was talking about. They're changing. You can see the quarry, downstream quarry up here is coming down in elevation. Now you can see the startup water pond beginning to fill 2 million cubic meters of water. And there it is. Didn't take long. So as of January, when we wrote the paper for the SME conference, which occurred in February, we had the status of the embankment. Here's a photograph in January 2020. You can see the 50-meter wide crest in these two photographs, the jacking header system. This system delivers overflow and whole tailings that are deposited on the upstream side of the embankment. This jacking header delivers the underflow that's placed and compacted on the downstream slope. And as of January, we had an embankment height of 199 meters above the foundation at the center line of the dam. And the current dam height as of today is 206 meters above the center line. One other thing that I wanted to point out is that the sand embankment reached the starter dam crest slightly ahead of schedule on September 1st of 2017. You remember I said that it was designed, the starter dam was designed to store 2 years of impounded tailing materials. And at the time that the sand reached the crest and we could begin building new freeboard above the starter dam crest, the impoundment tailings level was 8 meters below the crest. So it was a good comparison of the predicted and the actually experienced filling rate for both the embankment and the impoundment. This is my last slide. It's a photograph looking from the downstream quarry location toward the downstream slope. These zones are used to plan and execute the underflow deposition. And as you can see, the active deposition at the time of this photograph is in zone 1. Well, thank you. And at this time, I think we've got some time for questions.
Thank you, Jim, for a fascinating presentation. I would like to open up the question and answer period to our attendees. If you could use the chat panel, please, I will read the questions to Jim. And I'd like to remind our audience that this session is being recorded. It will be made available on the SME website in the near future, probably within about a week, when we will send you instructions on how to download the recording for your future viewing pleasure. The first question came quite early, and so you may have already answered it. What was the 5-meter freeboard based on?
It was based on deformation modeling, and we did those estimates a couple different ways. We used the FLAC 2D model that I described in the presentation, and I did mention that that indicated that there would be adequate freeboard. We also did an analysis using quad 4MU, and that was the maximum prediction actually of settlement due to the earthquake. It estimated about 2 meters of settlement. So based on that, we selected the 5-meter freeboard. So it's related to the deformation resulting from the maximum credible earthquake.
Thank you. The next question, I'm a bit confused about the flood handling requirement of design for the PMF versus design of the spillway for the 500-year flood. What happens if there is a flood that the spillway cannot accommodate?
Okay, so the tailing storage facility is designed for the probable maximum flood, and it has the ability to store the probable maximum flood runoff. I think the confusion comes in that the 500-year flood design that I mentioned is for the seepage collection sump that is located downstream of the tailing storage facility. And so that facility is designed to actually store the runoff from the 200-year flood, but the spillway for that seepage collection sump is designed for the 500-year 24-hour storm. And it's the reason for the lower design criteria is that the consequence of failure of the seepage collection sump downstream of the tailings facility has a much smaller consequence. And it's also consistent with Peruvian regulations, and I think with international practice.
Thank you. The next question, has the water balance model been updated? And if so, at what frequency is it updated?
That's a very good question. Both the material balance and the water balance are updated and calibrated based on actual throughput and delivery of tailing materials to both the impoundment and the embankment. And we've been updating the material balance and the water balance at least once a year, sometimes more frequently. But it's really important and key to do that. And it's important to the whole credibility of the material balance and the water balance, and the ability to make future predictions of raise rates and water consumption and so forth. So very good question.
Thank you. The next question, how is the potential of particle breakage of the underflow material evaluated, and how does it affect the design of the dam, in both hydraulic and mechanical?
Well, the way that we looked at the potential for particle breakdown was with these high stress triaxial tests that we performed, and we did gradations before and after the testing that showed that there was a very small potential for particle breakdown. I think a more significant source of particle breakdown that we see is actually between the time when the tailing material leaves the cyclone station, when the underflow leaves the cyclone station, and the spreading and compaction on the embankment are completed. And so I didn't cover this in the presentation, but we do see about an increase of 2.5 to 3% fines in the underflow between the time it leaves the secondary station and we've completed the spreading and compacting on the dam. So what we do there is the implication of that is that we have a maximum fine specification for the underflow after compaction of 15%. And so what that means is that we have to have a cleaner material with less fines produced by the secondary cyclone station. And so what we target there is a maximum of 12% fines in the underflow leaving the cyclone station. And we actually are usually able to manage that at about 10% or less. So I hope that adequately answers that question.
Thank you. The next question is quite similar, and you may have just answered it. The question is the underflow compacted or is it just hydraulically deposited?
Okay, I'll add a little bit to my prior answer. It is hydraulically deposited from the jacking header on the downstream side of the crest, and it's then deposited and spread in 30 centimeter lifts and is compacted with a combination of self-propelled smooth drum vibratory compactors and 6-ton compactors that are towed behind D6 dozers. The self-propelled compactors, don't think I mentioned this, but most of those have a weight of 12 tons. So all of the underflow is compacted. The compaction spec is 98% of standard Proctor.
Thank you. Next question. I saw an important fault altered zone along the valley. How was this feature considered in the design and risk profile?
Well, we did characterize that from the standpoint of age. It was certainly determined not to be active, so that was that was one of the contributors to the design basis and evaluation of risk. We did some, I guess, some special grouting in the foundation area at the location of that fault. We did stitch grouting. We added a couple rows of holes to those that I even, described in the presentation. So I think those were the primary considerations: seepage and the fact that the fault was considered to be inactive.
Thank you. Next question. How was QA and QC managed?
Okay. I'll describe a couple things. I mentioned that Cerro Verde was the contractor or the constructor for the major part of the earthwork, and Stantec performed the QA and the QC on behalf of Cerro Verde for the self-performed construction. There was, a large field crew. I mean, it was a large operation. It was 24/7 construction for 27 months. At the peak of the construction, Stantec had 75 people on the site doing construction engineering and QA QC. The QA QC for the contractor work, for the specialty contractor work, was done a little bit differently. Our philosophy is that the contractor should always have a quality control function within its organization. So the specifications required that. But in addition, Stantec did QA, I would say, at a QC level for the work that was performed by the specialty construction contractors.
Thank you. The next question. What is the difference between core and select core?
Okay. In terms of liquid limit and plasticity index, there was no difference. The specifications were exactly the same there. The difference between the core and the select core was really in the maximum size and in the fines content. So for the bulk of the core, the maximum size was 15 centimeters, and the fines content was 15% minimum. And for the select core, the maximum size was 1.5 inches, and the fines content was a minimum of 20%. And so we just didn't want to have the larger materials in contact with the abutment contacts with bedrock, where the larger materials, the larger particles would interfere with the bond that we could create between the core and the abutment. So that's where we specified the select core. And of course, it was much more expensive to produce, but well worthwhile. We had a lot more waste when we had to screen off the plus 1.5 inch compared to the plus 15, or 1.5 inch compared to 15 centimeters.
Thank you. The next question. I know for our attendees, we are running a little bit over time, but I think that is perfectly acceptable. The question is, can you comment on the monitoring program for the dam, the Straighter Dam, and the future ultimate dam?
I think it's Starter Dam, not Straighter Dam.
Straighter, okay.
Okay. Well, the instrumentation system consists of, I'm going to call them study sections. They're instrumented sections through the dam. One is at the maximum section, and then we began with 2 additional instrumented sections to the right and left of the maximum section. We have a system of vibrating wire piezometers, and they're monitored with an automated data acquisition system Cerro Verde and Freeport have actually upgraded that monitoring system using a canary system since completion of the starter dam. I guess that was completed about a year ago. So there's a pretty extensive system of piezometers. We have an accelerometer on rock, and we have an accelerometer on alluvium located downstream of the dam. So, and I mean, we get at least one measurable earthquake every month in Peru. So that's how we monitor the earthquake activity. I also mentioned that we have 4 shape acceleration arrays that were installed in the core. That was another method of instrumentation and monitoring that was used. We monitor the flow rates to the seepage collection sump in a couple ways. We monitor them at we have a V-notch weir, and we also monitor the pumping rates, pumping back from the seepage collection sump to the cyclone station, where we use that water for dilution water. I think that outlines most of the instrumentation that we use.
We have a couple more questions. The next one is also about cyclones. Can you confirm the primary cyclones were 15 feet and the secondary cyclones were 26? What was the basis of the cyclone diameter design for the secondary step?
Okay, so it's at the primaries, it's 15-inch cyclones, not 15 feet. And the
I
secondary,
apologize.
that's probably what was written. And at the secondary, we have 26-inch. So these are all Krebs cyclones, by the way. And during design, we used simulations that were performed by Krebs to design the cyclone number and size. But it was just to get the cut that we needed between the underflow and the overflow at the primary station. It was concluded that 15-inch would be more appropriate, and we also this might have been a subtlety, but I did mention this, that we have cyclo-wash installed at the primary station, which makes for more efficient use of water in getting that cut. And then similarly, we did simulation modeling to select the 26-inch size for the secondary station. So it's just a matter of, the experts, the Krebs of the world, knowing what works best and what's capable of producing the right quality and quantity of underflow for use in the project. I might just comment, though, that this is the central cyclone system. I think it sometimes we see individual cyclones on dams. It does have, in my opinion, an advantage in that you're controlling the pressure so that it's the same at all of the cyclones in the cyclone banks. And I think it's just much more easy to control the quality of the products, and even to maintain, for that matter, the individual cyclones, or to replace them when necessary.
Thank you. We've had several requests for you to repeat the time-lapse video again. Could you do that?
Certainly. Let's see. I find that I have to use escape again. It's a fascinating video, and I'm happy to do it again. I suspect I'm going to have to swap this again. Is that right?
Yes, that's correct.
All right. Okay.
Okay.
So here we go. I'll try to remember what I said during the first viewing, and maybe I can add something this time. So here you can see the quarry up here. Whoops, I'll get the laser going again. You can see the quarry beginning up here. It's coming down in elevation. The rock fill in the downstream zone. The core here. You can see these access roads to deliver rock from the upstream quarry coming up in elevation over time. Here we have a level fill surface. Everything's caught up to a level surface. In the background is a pipeline road from the seepage collection sump up to the cyclone station. Okay.
Excellent. Thank you. We have run out of time. Jim, thank you so much for sharing your expertise with us. Absolutely fascinating presentation. I'd like to again remind our attendees that the session was being recorded and you will receive instructions on how to download the recording. Jim, thank you again for sharing your expertise. Would you have any final comments for our attendees?
Well, I understand from Jackie that there was a full house and 200 participants showed up for the webinar, so I appreciate your interest. You know, I have a long career, about 47 years in the business, and this project, and actually even Quebrada and Lazada, which is only slightly smaller than this one, at the Cerro Verde mine, were really some of the most interesting and challenging projects in my career, and I just appreciate having the opportunity to share some of the lessons learned and some of the experiences with all of you. So thanks for participating.
And thank you for joining us on behalf of SME. Thank you to all of our audience for joining us. Have a safe day. And this ends today's session.